Here it's better. All right, so we, oh, that's time already to start. All right. So I really pleased by this opportunity to participate in such geometric topology conference with such a long tradition. So 40 years ago, it started in Texas. And for me, Texas also plays a very important role. So this was 40 years ago, Cameron Gordon invited me to present a colloquium talk in Austin. And I was at that time organized academic year, Topology 90, academic year in Ohio State in Columbus with Walter Neumann, Alan Reed, and Larry Ziebenman. So that was my first experience with Texas. And now I'm in Oklahoma, so University of Oklahoma. So that's, I'm gonna talk about non-rigidity for hyperbolic lattices, not necessarily cofinite. Actually, my attention will be to uniform lattices, therefore with corresponding to compact hyperbolic manifolds. And that's what I'm going to discuss. On one hand, the central topic of this meeting of geometric topology workshop is on hyperbolic nodes and links. Therefore, what we have such a link, and we able to introduce a complete hyperbolic metric on the complement of this link. Therefore, we are now dealing with a hyperbolic lattice in a isometry group of three-dimensional hyperbolic space. And this lattice, since we are dealing with the complement to link, this lattice is cofinite, not uniform lattice. And due to most of Margulis Raghunatha rigidity, we have that hyperbolic manifolds of dimension at least 3. If they are homotopy equivalent, they are isometric. So in that sense, Teichmüller space now is different from Teichmüller space for surfaces where hyperbolic metrics, consideration of hyperbolic metrics on surfaces is equivalent to consideration of conformal structures on these surfaces, Riemann surfaces. However, for hyperbolic manifolds, this is really big difference because from the point of view of hyperbolic metrics, if you fix a hyperbolic manifold of finite volume, then this manifold is unique. So in that sense, it is determines a hyperbolic lattice, and this lattice is unique up to conjugation. So, so in that sense, you may think that this hyperbolic lattice in three-dimensional hyperbolic space has a fixed combinatorial type of fundamental polyhedron. And due to Andreev rigidity theorem, this is 1970 theorem by Andreev, PhD student of Ernest Weinberg in Moscow. So this polyhedron is unique up to isometry. So that's, and now we are dealing with non-rigidity theorem by Bill Thurston. So who observed that if we have such not uniform hyperbolic lattice in dimension 3, then considering fundamental polyhedron for this lattice, you may make deformation of this polyhedron. So in that sense, in the complement of link, you have a different hyperbolic metric, locally looking like metric of hyperbolic space. However, this metric is not complete anymore because you are deforming your polyhedron. So in that sense, as a result of this deformation of fundamental polyhedron, you have now parameters for each link component. You have two parameters, which means you are making a discrete representation of fundamental group of this link complement of this hyperbolic lattice in a way that abelian rank 2 subgroups corresponding to links, components now are homomorphic images as virtually cyclic groups. Therefore, you're making then surgery on this component of link and gluing instead of punched torus neighborhood of this component as now solid torus inside. So you have then surgery, and this then surgery depends on two parameters. So therefore, what Thurston proved that you have a variety of such discrete representations of hyperbolic lattice, and this variety has big kernel of this homomorphism with discrete representation. So, but this deformation is working, first of all, only in dimension 3. In dimension 4, Raghunathan proved that there exists a local rigidity, that you, in the sense of variety of representations, you cannot approach such embedding of hyperbolic lattice by not exact bijective representation of hyperbolic lattice. But in Thurston non-rigidity theorem, you have such representations which are arbitrary close approach the embedding, and corresponding manifolds, hyperbolic manifolds. They can be compact. They have hyperbolic volume strictly less than hyperbolic volume of the link complement. And they approach this inclusion, these representations, arbitrarily close. So therefore, it is impossible due to rigidity in the sense of local rigidity, in the sense of algebraic geometry, algebraic topology, and also there is a global rigidity. I just considered the behavior of ends of this manifold and prove that in a dimension bigger or equal 4, such deformations are impossible even in global sense, not just locally, local rigidity. So there is global rigidity. So therefore, we will look at this situation from the point of view that let's consider some uniform hyperbolic lattice. Therefore, this hyperbolic lattice corresponds to compact hyperbolic manifold or orbifold. And now you would like to deform this hyperbolic lattice. And we know that in the sense of if result is again hyperbolic lattice, that this deformation is impossible because of most of Margulis rigidity. However, I would like to make discrete representations of this hyperbolic lattice in dimension 3 to make such representations with non-trivial kernel of this homomorphism. So this is part of my results here. So we will look at this situation, first of all, from the point of view of varieties of conformal structures on closed hyperbolic 3 manifolds. So generally, you may consider even n-dimensional manifolds, and you have such variety. Now, since we're talking about conformally flat structures, we consider now these discrete representations into isometries of n+1 dimensional hyperbolic space. So therefore, these isometries act on the infinity of hyperbolic space by Möbius transformations. Therefore, now we are talking about conformally flat structures on the initial hyperbolic n-dimensional manifold. So here it was conjecture by Borel and Woloch that such conjecture was on the level of homology group, that whether this is possible or not. So this was my old result, who knows when, this 1977, just a few years after my PhD, I proved this. And but now we may look from a different perspective. Now, if you consider such n-dimensional hyperbolic space as n-dimensional, say, codimension 1 hyperplane in n+1 dimensional space, then we consider such Kleinian n+1 dimensional manifold, which is quotient of n+1 dimensional space and the domain of discontinuity of this lattice at infinity. So therefore, this domain of discontinuity for initial lattice looks like complement of n-1 dimensional sphere. And this Kleinian manifold looks like product of initial n-dimensional hyperbolic manifold and closed unit interval. So, but now we may consider analogies of this product from homotopy or even homology point of view. So in that sense, you may look at n+1 dimensional manifold, or in our case of dimension 3, we consider 4-dimensional cobordisms, where the boundary of this 4-dimensional cobordism are homeomorphic to initial hyperbolic 3 manifold. And we may consider such cobordisms not just trivial as products. You may consider them in the sense of homotopy cobordism, H cobordisms, or we may consider them as homology cobordisms, which means that inclusion of each boundary component induce homology equivalence to such 4-dimensional manifold. So, and I constructed such non-trivial homology cobordisms. And here we have such 2-dimensional widely knotted sphere embedded in a 3-dimensional space. And this sphere bounds 3-dimensional ball, widely knotted ball. And this wild knotting happens on a dense subset of the boundary of this ball. So therefore, now we have conformally flat structure on initial 3-dimensional manifold given by action of our hyperbolic lattice inside of such wild 3-dimensional ball. So in that sense, we are dealing with 4-dimensional cobordism, which one boundary component has homotopy equivalence to 4-dimensional manifold, and another boundary component is covered by the complement of this wildly knotted ball. Therefore, the embedding of the second component in this cobordism is not homotopy equivalence, but still homology equivalence. So by using Meyer-Vietoris exact sequences and Alexander duality, we were able to calculate homology group and prove that such in such situation we have homology cobordism, and this homology cobordism in dimension 4 is special cobordism because in dimension 4 there is famous Sergei Novikov conjecture he formulated in connection to classification of rational classes, homotopy classes. And so in that sense, dimension 4, when you cannot classify cobordism by homotopy groups. So, and if both components of this action of the group are not only invariant for the image of this homomorphism, but also simply connected, then cobordism would be homotopy cobordism. So far, there is no example of that. So, but with respect to this, you come immediately to a question. What happens if you're dealing with a cobordism, four-dimensional cobordism, where both boundary components of this cobordism, they're pretty symmetric, not like in the previous situation like this, that one boundary component is covered by a three-dimensional wall, and another boundary component is bounded by infinitely generated domain with infinitely generated fundamental group. So therefore, we get to a situation where this was a conjecture that if you have such four-dimensional cobordism with the symmetric in topological and geometrical sense boundary components, then is it possible to have in fact H cobordism? Possibly not trivial, so which will answer very intriguing questions in that way. So, however, I was able to negatively answer this conjecture, my conjecture, and I was able to construct hyperbolic four-cobordism with boundary components highly symmetric to each other, not only in topological sense, but even in the sense of action of fundamental group of this cobordism. So what symmetricity I mean here, that we now have two components of discontinuity set of group G, and we have a fundamental polyhedron for such action in one component, and we have fundamental polyhedron for such action in the second component. So, and these two polyhedra are completely symmetric. So they are the same in combinatorial sense, and even magnitudes of dihedral angles are the same. So, but still the cobordism constructed in that way is not trivial. And the presentation which produce such group G, fundamental group of four-dimensional cobordism, the presentation has infinite kernel. And I was able to calculate this kernel. It appears to be that this kernel is just a free group on three generators. So therefore, you have such on three generators, and each element of this free group is mapped by our presentation to trivial element. So, but by some reasons, I was eager to make such discrete, not faithful representations of uniform hyperbolic lattices with kernel, arbitrarily large kernel, in the sense that this kernel would be not free group on three generators, but it would be free group on arbitrary many generators. Therefore, what we're talking about now, that to produce such presentations where we are dealing with when we are dealing with groups with hyperbolic lattices in three-dimensional hyperbolic space, uniform lattices, which behave like groups presentations in Thurston non-rigidity. But now we are dealing not with confined hyperbolic lattice. We are dealing now with uniform hyperbolic lattice. So, and to do this, I developed conformal enhancement of Gromov-Piatetski-Shapiro interbreeding construction. So what we're gonna do, okay, here. So what we're gonna do, let me remind what was Gromov-Piatetski-Shapiro interbreeding construction. They use this to construct non-arithmetic hyperbolic lattices in any dimension, no matter dimension 3, 4, 5, 1 million. So, and what they did, they looked at n-1 dimensional sublattice in the given lattice. And they consider another lattice where n-1 dimensional sublattice is isometric to the first one. Then they glue this to hyperbolic lattices along isometric sides and obtained result going to be uniform hyperbolic lattice in dimension n. But this lattice, if you just follow some restrictions, not going to be arithmetic. It's going to be non-arithmetic because in n plus 1 dimension, the size of these two lattices will be different. So now what I do here, my conformal interbreeding will use that idea by Gromov and Piatetski-Shapiro in conformal category. I now consider deformed hyperbolic lattice, and I consider deformation of another hyperbolic lattice in the sense of conformally flat structure. So therefore, by using combination theorems like Musket type combination theorem involving amalgamated free products and H&N extensions, I'm able to glue these conformal deformations along conformally equivalent sides. So in that sense, you may think that in the n-dimensional manifold, I consider some totally geodesic submanifold, suborbifold. And for another manifold orbifold, I consider the same totally geodesic subsection. And to make these subsections conformally equivalent, I'm able to glue these two objects together. So in that way, I'm able to make not faithful discrete representation of hyperbolic lattice acting in three-dimensional hyperbolic space with kernel of this representation to be arbitrarily large free group on a given number of generators. So how much time I have is probably the time I should finish. I just will show you some idea how to construct such symmetric hyperbolic for cobordisms. Just few words. Imagine that you are dealing with a tennis ball. So if you look at tennis ball, you see that this tennis ball has white loop separating it into two symmetric parts. So now I would like to consider 4 vertices on this tennis ball. Therefore, you have 2 pairs of such vertices. And now I look at this ball, not as ball, but as topological ball. And it is union of 4 round balls, which are mutually orthogonal to each other. The boundary spheres are mutually orthogonal to each other. So in that sense, now we have to embed a 2-dimensional disk in the complement of this ball, such that the boundary of this disk is glued to that tennis ball along this white loop. And now we may have such situations that you see you have four initial balls. These are three coordinate planes, and the fourth ball is bounded by sphere centered at the origin. So now we have this loop as white loop on the tennis ball. Now it is a bold loop here, and this bold loop is bounding embedded disk. So embedded disk is kind of built up from hyperbolic blocks. That's the method I use successfully in my constructions, so-called block building construction, that I produce something like Lego pieces, only hyperbolic pieces of Lego, which you obtain by cutting hyperbolic manifolds along totally geodesic surfaces. And then these pieces, I make conformally flat deformations to look like unit disks, or say not disk, sorry, unit cubes, bigger or smaller cubes, and I can make some idea, geometric idea, induced by my topological needs. That's what always in geometric topology people do, like Fox-Artin arc, how to use this Fox-Artin arc to produce that quasi-symmetric embedding, which produce such wild embedding of ball with wild knotting on dense subset. So I use also that block building construction. So therefore, in that way, I'm able to make such situation and to make sure that now each this cube is really a result of deformation of hyperbolic piece from a round three-dimensional ball, where you have hyperbolic lattice, initial lattice working at. So and that way, it gives me a tool and to prove how the discontinuity set of such image, discrete representation image of my hyperbolic lattice looks like. So I prove that this two invariant component for action of this group defines a Higgs splitting of this sphere along infinite genus, say, common boundary. So that's, I guess I don't have time anymore. Is it, Nathan?
Yeah, I think we're about there. So if
okay, I finished just to provide some maybe references where you can find more about such construction in details. So some of them are published, and the last reference now in work. So that's going to be a new big book I'm writing right now on dynamics of discrete group action, also in de Gruyter series for advances in analysis in geometry. And it's like my another book was published by de Gruyter in Exposition of Mathematics almost 20 years ago. So I have like kids, you know, like dozen of books published around the world.
Well, thank you, Boris. If everyone wants to give some virtual applause, and if there are any brief questions, we can bleed into the break a little bit. Otherwise, I will see you back in about half an hour. But we can take a few questions.
That's actually an advantage to be the last before the break. So, and actually, it has several applications in geometric analysis for investigating, for discovering new properties of quasi-regular mappings. Quasi-regular mapping is just a three-dimensional analog of analytic mappings in a complex plane. So like they are up to branching set are quasi-conformal mappings with bounded distortion. And on branching set, you may have the same behavior as analytic functions may have at branching points. So that's what very kind of popular and very many applications in science such mappings have. So for example, to prove advanced results in Fatou problem or Lavrentiev problem or something like this. So there are many properties proved here, answering some well-known conjectures like Matty-Warren formulated conjectures in 70s, 80s. So that was solved in number 8 and number 9. Or to look how Fox-Artin knotting of three-dimensional balls can be achieved, that this knotting may have arbitrary number of finitely many types of Fox-Artin arc. So Fox-Artin arc is arc which has periodicity of knotting. So you have kind of one knot and then another knot and then another knot and then infinitely many, and you add the point at the limit. So in that way you got Fox-Artin arc. And if you consider now not just a knot, not arc, but if you deal with the ball, then you have Fox-Artin ball. So that's and actually one of reference I put on chat has my paper in '89 in Finnish proceedings of Finnish Academy of Science in Mathematics. So that for quasi-symmetric embedding of three-dimensional ball, closed three-dimensional ball, which is equivalent with respect to action of hyperbolic lattice in the round ball, obviously. So that would be another interesting use.